Hey guys, how you doing? So welcome to the fourth video in this chemistry series. In this video, we're going to explore what covalent bonding is, some of the properties, and how we figure out these covalent bonds. All right, so let's jump into it. Okay, covalent bonds. So covalent bonding is very different from ionic bonding. So in the previous one, ionic bonding occurs between a metal and a non-metal, where you have one atom that is going to give away its electron and one atom wanting to take electrons. Now, what happens if you have two atoms where neither of them are going to want to give and both of them want to take? Which means if you're, for example, working with chlorine and another chlorine, both have 7 in their outer shell and 7 valence electrons, and so they're not going to want to give up 7 of their electrons to become stable. They're going to want to just take 1, right? And so for covalent bonds, it actually occurs between a non-metal and another non-metal, where both non-metals are going to share the electrons, right? To become stable, it's a bit of a compromise because they will share the electrons that they have with one another, and the electrons are going to orbit around both the nuclei, right? So this little diagram here that's kind of running around in circles is an example of hydrogen. Now, hydrogen has 1 electron in its outer shell, and because it's in the first shell, the first element, it only needs 2 to become stable, which means it wants to gain 1 more, okay? So in this particular case, if hydrogen comes in contact with another hydrogen atom, they both want to take 1 electron from each other, and so as a bit of a happy medium, they're going to share those electrons with one another, and the electrons end up orbiting both of them in this kind of figure 8 motion. So you can sort of see there the electrons orbiting around both, representing this covalent bond. Okay, here's another example. So if you have carbon and oxygen, some of the electrons are going to orbit around both atoms. Others aren't. Okay, so in this particular case here, carbon has 4 in its outer shell, which is represented by the green dots in the outer shell, and oxygen has 6 in the outer shell. 1, 2, 3, 4, 5, and 6. And then what's going to happen is, because oxygen only needs 2 and carbon needs 4, carbon's going to bond with 2 oxygen atoms to become stable, and this electron here, this one here, this one here, and this one here, these 4 electrons belong to oxygen and will only orbit around oxygen. But these last 2 right here, they actually belong to oxygen and they belong to carbon. And so what happens is these 2 are going to orbit around oxygen for half the time and around this carbon for half the time. And the same with these 2 green electrons here as well, that they belong to carbon, but they are also going to orbit around the oxygen there, which means these 4 here technically belong to both the carbon, the carbon here and the oxygen here. Yeah. Now you can say the same thing for the 4 on this side, and therefore temporarily in this particular case here, carbon actually has 8 in its outer shell. You can see 4 on one side and 4 on the other side, but 4 of them are shared with this oxygen and the other 4 are shared with this oxygen, right? And so therefore technically they all have a full outer shell. Okay, now we're going to break that down into a series of steps so that you guys can sort of figure out, okay, well, how do we actually develop these covalent bonds? Let's take chlorine gas, for example. Chlorine gas is actually 2 chlorine atoms that have joined together in a covalent bond. Now, in most cases, actually, a lot of non-metals, especially if they are occurring naturally as gases, will bond together in pairs. And so if it's chlorine, you'll have 2 chlorine joining together. If it's oxygen, you often see oxygen being represented not as O, but as O2. O2 meaning that there's 2 oxygen atoms that have bonded together in a covalent manner. If it's hydrogen gas, it's H2, which have been bonded together. If it's fluorine gas, for example, it'll be F2 joined together as well. Yeah. But in this particular case, let's take a look at chlorine. So 1 chlorine atom, remember that once again, you're still using the atomic number, the configuration, and to get to the valence electrons, right? 1 chlorine atom has 17, the atomic number of 17, and its electron configuration is 287 with 7 valence electron. So each chlorine needs 1 electron to become stable. So what that means is they are going to then share 1 electron with each other, forming a covalent pair. right? If I was to represent it with X's and O's to tell you which one belongs to which, here's chlorine. For the sake of this diagram, I'm only showing the outer shell. Yeah, I'm ignoring the 2 and the 8 shells, and I'm only looking at the one with 7. So this chlorine atom here is represented, the electrons are represented with the circles, and then this one here is represented with the X. You can see there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, see these 2 electrons in the middle. They are what we call a covalent pair of electrons. Yeah, which means if it's a covalent pair, it will orbit both the atoms that it is paired to, which means both of these electrons will move around this one for half the time and this one for half the time. So technically, right, this X belongs to both the original chlorine atom that it was with, and it belongs to the other one, which means you can now count it as part of the chlorine on the left, which means chlorine technically has 1, 2, 3, 4, 5, 6, 7, 8. Okay, now you can say the same thing for this O, or this circle, belonging to the chlorine on the right. 1, 2, 3, 4, 5, 6, 7, and 8 there. Okay, so that's what a covalent pair looks like. If I was to draw it using the dot diagrams, a covalent pair is always represented by a stick. Yeah, a stick tells you that there is 2 electrons in there. Yeah, not 1, 2 electrons in there, right? And so every time you're counting the dots in your electron configuration diagram, you need to count the sticks as 2, and they belong to both atoms that they are joining together. Yeah, so if I was to count it, it'll be 1, 2, 3, 4, 5, 6, 7, 8 for this one over this side, and the same for this one over on this side here as well. 1, 2, 3, 4, 5, 6, and then 7, 8. Okay, now you can draw it a few different ways. Yeah, the original dot diagram will look like this, but the stick diagram would simply show with the stick in between the 2, and sometimes they even ignore the remaining electrons that are not covalently paired together. Okay, and so the equation for that is you simply have Cl minus plus Cl minus forms Cl2. Remember the subscript number representing the number of atoms within the one molecule or compound. You've got 2 there belonging to chlorine. Okay, now hopefully you'd be able to recognize as well that when you are forming these pairs, you can't possibly have more than 4 sticks joined together to an atom. Yeah, because each stick represents 2 electrons covalently bonded to another atom, and so you can never have more than 4 because that atom only needs 8 to be stable. Okay, so that's something that's worth keeping in mind, and it will help you track how you are going to put the bonds together. Okay, let's take a look at another example. So let's look at oxygen gas. So oxygen gas is O2. There are the stats for your oxygen atoms, each with a valence electrons of 6. And if we were to show it in diagram, that's what it would look like. Now you will notice oxygen, rather than having 1 pair of electrons joining together with the other, has 2. And so you would expect that the number of valence or electron pairs that the oxygen atoms will have will be 2 electron pairs, meaning there are 4 electrons in total being shared by both oxygen. Yeah, so this oxygen represented with the X's have 1, 2, 3, 4. These belong exclusively to the oxygen on the left, but 1, 2, 3, 4 will orbit around both. Okay, and therefore oxygen, this oxygen on the left here will have 1, 2, 3, 4, 5, 6, 7, 8 outer shell electron. It is now stable, and the same can be said for the other oxygen atom. Okay, and that's how you represent it with a stick diagram. Yeah, you've got 2 covalent pairs there showing 4 electrons being shared by both. Okay, and so it's quite simple. You count the number of sticks, and then any remaining amount that isn't joined together by a stick is actually done with a dot. Okay, so if you're not sure, often what I would do is I would actually draw the dot first. So if you were to draw oxygen, you would draw 1, 2, 3, 4, 5, 6, and you do the same for the other side. 1, 2, 3, 4, 5, 6, and then you just draw a line to connect the 2 dots together so that it makes sense. Okay, that's what oxygen would look like in a diagram, and the equation, once again, O2 minus plus O2 minus gives you O2. Okay. Now let's look at one with a slightly different mix. Okay, so in this case here, before I show you what it's going to look like, let's take a look at methane. Now methane gas is the same kind of gas that you produce in your farts actually. It's made up of 1 carbon atom and 4 hydrogen atoms, and they're joined together. Now at this point, sometimes it might seem a bit confusing as to, well, how are we going to put this together? Are you going to have carbon, hydrogen, 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 or are you going to have carbon, hydrogen, hydrogen, and hydrogen, hydrogen, or is it going to be a square where they're joined together? It's hard to tell what kind of structure it's going to have until you start drawing it and you start seeing what it's going to sort of form as you practice it. Okay. Now, the way to do that is you need to make sure that the number of electrons that each atom needs is counted every time you do it. Okay, so each carbon atom requires has 4 valence electron and therefore requires 4 more to become stable, but each hydrogen is only going to need 1. And so what you're going to get is you're often going to get the one with the most with the middle amount of valence electrons sitting in the middle, right? And so the carbon in this particular case actually forms the backbone, right? It sits right in the middle, and what happens is the hydrogen are going to bond together with the carbon. All 4 of them are going to stick together to hydrogen like that, and what you get is the carbon sits in the middle, and there are 4 electron pairs coming out from carbon, and each one joins together with hydrogen to form a covalent pair that is now covalently bonded. And so it actually forms what we call a carbon tetrahydride, tetra meaning 4, hydride for hydrogen, otherwise known as methane. Okay, now this might take a bit of practice and it might take a bit of time for you guys to wrap your heads around, but that does kind of show you how methane bonds together. Okay, and if I was to draw the stick diagram, that's what it would look like. All right, the chemical equation for it will be C4 minus plus H plus will give you CH4. Okay. Now the last part, we're going to take a look at the properties of covalent bonding. Because of the nature of covalent bonds are different from ionic bonds, you're going to get different properties. Yeah, ionic bonds, they're really strong, and they're really strong because of that tight bond between the pluses and the minus in the ions. But they're also really brittle, which means that if you knock the ions out, repels from one another, and because of the negative anions, you can dissolve them in water and it conducts electricity. The covalent bonds are slightly different for once again. Okay, so covalent bonds tend to have a lower melting and boiling point, right? This is because the intermolecular forces are weak. What that means is because the electrons orbit around both atoms, it's not as strong and is not as attracted to the protons in each atom, because it's spreading half of its time in one atom and then the other half of its time in the other atom. What this results in is that it's more easy to break those atoms apart than it would be for an ionic bond, for example. And therefore we say that the intermolecular, inter meaning between the molecules, the forces between the molecules are weak and can be broken apart easily. Okay. The advantage, however, or I guess you can call it a bit of an advantage, is that it is much more squishier than the ionic bonds, because there's no positive negative opposite attracting and then being misaligned when you hit it with a hammer. And so as a result, what you end up getting is that you get a more softer, malleable, squishier compound as a result. Okay. Because the bonds are slightly weaker as well, covalent compounds tend to be a lot more flammable. So a good example is if you think about sugar. Sugar will burn quite easily because it is a covalent bond. Salt won't burn, and it is much less flammable. Okay, you can't dissolve it in water as well as you can with salt, because the anion and the cation doesn't break apart. What actually happens is if you put sugar in water and you mix it, what actually happens is it dissolves in it, but it doesn't break apart in the water. You're not going to get the carbon and the hydrogen and the oxygen breaking apart. You're just going to get tiny sugar molecules that are too microscopic for you to see. And then finally, it doesn't conduct electricity in water. Yeah, whereas salts will. Yeah, so Yeah, so those are the difference in there. Okay, so so that's that. Hopefully you guys learned something new in this lesson, and I'll see you guys next time for balancing chemical equations. All right, see you then.